Okay, so one thing I want to do before moving on with again solving ODEs involving the step function, I want to show you how you actually go from a piecewise function actually described or given by a graph and then written in terms of the step function. Suppose, for example, the input in a differential system is given by a graph to begin with, right? So I mean, in that case, there is an extra step in the sense that you have to write your piecewise function from the graph and then use the step function. So for example, here I show you a graph which connects these points from 0, 2 to 2, 0, and then it's 0 between 2 and 3, and then it's back to 2 between 2 and infinity. So how do you actually use, how do you write this function with the step function? Well, you got to take your time to write these lines, these pieces in terms of t. So the first piece is a line. So to write a line, of course, you need to write the equation of a line connected, in this case, the point 0, 2 with the point 2, 0. So just do the whole work with the point slope form and so on and so forth. I mean, the slope would be 0 minus 2 over 2 minus 0, which is minus 1. And then using the point slope form, and let's say using this point 2, 0, I get y minus 0 equals the slope minus 1 times t minus 2. So y equals minus t plus 2. So my function will be minus t plus 2 in the beginning between 0 and 2. So then you can write your function as a piecewise defined function, which is, like I said, minus t plus 2 when t is between 0 and 2. Then the function should be 0 between 2 and 3. And then the function it's equal to 2, a constant, if t is greater than 3. So in some problems you have to do this extra step before you approach the problem with the step function. How do you write the whole thing via the step function? Well, just like I told you before in the beginning of the lecture, you start with the first value and then introduce step functions at each point where the function changes. The first time it changes is that it's at time t equals 2. How do you change the value? Well, you're gonna cancel the previous value. If it was minus t plus 2, to cancel that, I add t and subtract 2 and put a new value in, which in this case is just 0. Finally, at the next point the function changes at times equals 3. Cancel the previous value, which means there's nothing to do. It was 0 minus 0 is the same thing, and put the new value in, plus 2. So let's say now I want to find the Laplace transform of this. I actually made it so that it's in the proper form for the delay theorem. If it's not, you have to do some other algebra steps. But now, when you take the Laplace transform, it's very important to understand when you need the delay theorem. Again, really pause for a moment and look carefully at these terms and realize that only the middle guy deals with the delay theorem. This one, this one, this one are just applications of formulas from the table. Linearity property and formulas from the table. Well, this is also in the table, but all I'm saying is that this is the only piece which requires the delay theorem that deals with that substitution process. Let's try to do this in one step, because it's not that difficult. So L of t, let me write it down again here. L of t to the n is n factorial over s to the n plus 1. Okay, so L of t is 1 over s squared. So this is minus 1 over s squared. L of 2 is 2 over s. This one now deals with the delay theorem. So let's do it in our mind. Substitution t minus e a with t. So t minus 2 becomes t. L of t, again, is 1 over s squared. And this becomes e to the minus 2s. Substitution, take the Laplace. T minus 2 becomes t. L of t is 1 over s squared. And this is just 2 times the Laplace of step t minus 3, which is e to the minus 3s over s. And so that's the Laplace transform of this function. So let's not forget at this point that the main goal of this discussion is to solve differential equations, right? So I mean, let's see how we do this in the context of using step functions. Well, the good news is that you do it just like you did it before. The only difference is that as soon as you involve the step function, the delay theorem pops its head. The ugly or the nice head, depending on how you like it. So let's start with, well, let's see which one first. Let's start with the first order ODE. So let's write it as the subtitles. ODEs with step function. And you can have more than one, by the way. So for example, let's say I have to solve y prime equals step t minus 1 minus 7 times step t minus 3. And remember, we need initial conditions. So let's say y of 0 equals 5. What do? We take the Laplace on both sides. L of y prime is L of step t minus 1 minus 7 L of step t minus 3. And again, have the table in front of you. S times big Y minus y of 0, which is 5. And this would be equal to e to the minus s over s minus 7 e to the minus 3s over s. So you could tell already that once we get to find y, and then revert back to little y via the inverse Laplace, we will have to deal with the delay theorem, because you will end up with quantities like this, right, in that form. Okay, so move the y to the right and divide by s. Okay, so therefore big Y is 5 over s minus, plus 1 over s squared e to the minus s minus 7 over s squared e to the minus 3s. The two terms that require the delay theorem are these guys. And for the record, let's put it here that the L inverse of 1 over s squared is t. You're going to do that basically at each step, except the substitution is different when you go from right to left. So look carefully here. When I take the inverse Laplace, that's 5, because the inverse Laplace of 1 over s is 1. Now the delay theorem, pay attention here. Inverse of this is t. Substitution t with t minus 1, because we have minus s here. So this is going to be t minus 1 step t minus 1. Moving over with the linearity property, 7 comes out. The inverse of 1 over s squared again is t. Substitution t with t minus 3. Yeah, when you write it like this. So t minus 3 step t minus 3. And this is your answer. Okay, so 5 plus t minus 1 step t minus 1 minus 7 t minus 3 step t minus 3. And I want you to pause for a moment and notice that it will make sense in the fact that your answer looks like that, given the way the input is given here, the input in the ODE. What does it say? Imagine this is a physical system. What does it say it happens with the physical system? It says that nothing happens until t equals 1. What's your initial condition? That's 5, right? Until t equals 1, the function is equal to 5. Doesn't change until these step functions take effect. And notice the solution reflects that. Okay? These functions are 0 until t equals 1, so that's not a surprise that the function is equal to 5, because that's the initial condition, until something happens to that system. You know, in that case, plus 1 and then minus 7 when time changes at 1 and 3. Then something happens at times equals 1, something happens at times equals 3. Okay, so I mean, the solution basically reflects, roughly speaking, what happens to the input of the equation. Let's do another one. Let's do a second order this time. And there will be more examples in the notes, by the way, that you should actually go over. let's do a second order, and again one that will force you a little bit to go over some algebra steps before you write the final answer. So let's do this one. Let's say you have to compute y double prime plus 4y equals step t minus 3. And here we need two initial conditions. Y of 0 equals 0. Y prime of 0 equals 1. By the way, if you think of this as a mass spring system, this is a case without damping. And then the external force acts 3 seconds or 3 minutes later, whatever the time unit is. So imagine that you have some initial velocity, no initial displacement, the object starts to move on its own, and then there is going to be something that happens at times equals 3. Okay, so take the Laplace on both sides. L of y double prime plus 4 L of y, and L of step t minus 3 is e to the minus 3s over s. Carefully look at the formula sheet, and you get what? You get s squared big Y minus s times y of 0, which is 0, minus y prime of 0, which is 1. That's the formula for Ly double prime, and that's 4 plus 4 times big Y e to the minus 3s over s. Factor y on these guys and move the 1 to the right. And then we're going to have to divide both sides by s squared plus 4 to get y by itself. So don't rush this example. I have some important comments to make. So big Y is 1 over s squared plus 4 plus 1 over s times quantity s squared plus 4 e to the minus 3s. Okay, so the most important comment I want to make is that to resist the temptation to combine these fractions, even though you see those common denominators there, I mean the temptation to pull out or to combine, to write the common denominator here and multiply this by s and add. So the common mistake, let me write it here, is people to combine this and they end up with something like that. Well, that's not in the frame. So they end up basically with let's see, s plus e to the minus 3s on the top. That's not going to help. That's not going to help. So just don't do that, because let me actually get out of the way from here, because this deals with the delay theorem. So when you take the inverse Laplace, you need to use the delay theorem for this one. And this one is just straight from the table. So there are two different techniques to actually deal with these two terms. You need to take this separately and use the delay theorem. So it's not going to help to combine this together. This will be an application from the table. I'm going to need 2 on the top to match it with sine of 2t. That's going to be an easy task. This one, on the other hand, we need to do some work to split 1 over s times s squared plus 4 into partial fractions, which in this case is a over s plus bs plus c over s squared plus 4. So we need to do a little bit of work here in order to finally take the inverse Laplace. As part of the application of the delay theorem, we need the inverse Laplace of that coefficient. So let's just do the split. So this is going to be equal to a, so 1 on the left is going to be a times s squared plus 4, and then s times bs plus c. This will be actually easier than you may think, because some of the coefficients can be found right away. So the coefficients of s squared is a plus b, that should be 0. The coefficient of s comes on one position only. There is no s on the left, so that should be 0. And finally, the constant for a should match 1. All right, so c equals 0, a is equal to 1 over 4, and automatically b is minus 1 over 4. from the first equation. So this quantity, this fraction 1 over s times s squared plus 4 is in fact 1 over 4 times 1 over s minus 1 over 4 times s over s squared plus 4. Okay, so when we take the inverse Laplace of this, let's write it here. That's going to be 1 over 4, because the inverse Laplace of 1 over s is 1, minus 1 over 4 cosine of 2t. Yeah, s over s squared plus 4 goes back into cosine of 2t. Okay, now let's put all pieces together. Going all the way back here, little y is the inverse of this. Again, slowly. The inverse of the first part comes from the table right away. That's 1 over 2 sine of 2t. This piece is the delay theorem. Here is the inverse of this, which I just found, but with t replaced by t minus 3. So all I have to do here is to replace t inside the cosine with t minus 3. And of course, multiply everything by step. I mean, this portion here is multiplied by step t minus 3. So basically, don't forget to make that substitution as a process in the when we do the delay theorem. And be prepared that the delay theorem appears in one term only in the whole expression. So let's continue on the next part with finally the so-called impulse function, which is actually probably the most interesting application that we're going to go over of the Laplace transform, and finish up with some other examples of differential equations involving these special functions. So stay tuned.